Okay, in today's lesson, we are going to look at integration, which is finding the area under a graph. Now, just to recap, if you have a XY plane, a Cartesian plane, if you have a function, so let's draw our most basic function. So we'll do let's have this function here. So this could be a function y equals x. And we know y is x because if we have 1 there, then x is 1, y is 1. Also, this can be written as f of x equals x. And of course, f of x is the same as y, but f of x allows us to then do different graphs. So if you were to have two graphs on the same plane, so say you wanted like a graph like that, then this could be g of x. All right. So that's why we label things f of x rather than just y. So when you first started maths, we had y. Now we're looking at f of x and g of x. Now, when we did differentiation, we were looking at finding the slope of a graph. And so if you wanted to find the slope of this graph, you would find f dash of x. And so it would look like that. And if if f of x equals x, then f dash of x would equal 1. All right. If you don't know how I did that, I'll put a link to the differentiation video, the introduction to differentiation, in the link below. But you need to know that before now we start with integration. So with differentiation, we were finding the slope. Now we're going to be doing integration, which is where we find the area under a graph. Okay, so I'm going to just delete the first two, and let's just work with our most basic graph now, which is the f of x graph. So we are wanting to find the area. So let's look at the area under the graph over here from the 0 to 1. And so we see that it's a triangle with a height of 1 and a base of 1. So we know that if we were to just work it out using this triangle, we would say, well, the area is equal to a half base times height, right? So area equals a half base times height. The base is 1, and the height is 1. And so a half times 1 is a half. And if we were to work out the area to 2, let's do a different one. So for 2, so it will be 2 and 2. Then you have the area would be equal to a half, and then the base would be 2. And then the height would be 2. And so we would get a half times 2 times 2, which is 2. And so what we should just say units squared here. And units squared because it's an area. Now, notice that when we go along 1, so it becomes, if we were to find the area here at 0, it's nothing. And so it goes from a half to 2. And if we went to 3, it would be a half times 3 times 3, which would be 4.5. And so it's getting sort of exponentially bigger, if you notice. As you move across 1, the area is becoming much bigger. And we can see that because if we were to go to 3 here, I won't do the actual calculation, but we can see that it's a much bigger triangle. And so you could fit lots of these pink triangles into this green triangle. Okay, so is there an easier way to do this? Is there a way to calculate your area using a formula? And there is. And this is what we call integration. So let's look at some notation first. So when we find our slope, remember we said f dash of x. When we integrate, what we're going to do is we're going to, and let's use, we did the first area in pink, so let's do it in pink. So we'll say, we say this. Okay, so we use this weird S sign, and that means find the integral of f of x. And so there's a formula that we do. Now, if you remember the differentiation formula, you take 1 off the exponent and then multiply by the exponent. So although I said you should look at the video, I'll just remind you, if it was say x squared, our derivative would say exponent times the front and then take 1 off the exponent. So exponent times the front. So there's 2 times the 2 goes 2. And then 2 minus 1 is 1. So, and then of course, when we have an exponent of 1, we just write. That's the default, so we don't need to write the 1. So this was our differentiation. As I said, watch that video if you don't know, if you got lost there, because you should know that. Now, the integral is a little bit different, because what we do is we, instead of subtracting from the exponent, we add to the exponent, right? So if our f of x, right, so our f of x was over here, right, yellow. So if our f of x was equal to x, what we do is we add to the exponent. So if I add 1 to 1, I get x squared. Okay, and then what we do is we divide by the exponent 2. Okay, so we add to the exponent and we divide by what we add. So this will be the answer. If our so what we do is we actually, let's look at that as a formula. What we'll say is f of x, and we'll say, what if this was an n here? So the exponent was n. So then you just sort of say n plus 1, and then over n plus 1. Okay, and so that's what we would end up with. Oopsie. I'm going to delete this. Yes, why is it not going away? Sorry. I'm just going to do it the long way. Okay, just put back over it there. Okay, so this is what we'd end up with. So let's look at a few examples before we go into a bit more detail. So let's say that we wanted the integral of, say, x squared. I'm putting the 2 because the exponent is key here. Because what we do is we add to the exponent, right? So it's 2 plus 1. And then what we're doing is we're dividing by 2 plus 1. And so our answer would be x to the 3 over 3. Right. So if you find that the exponent of the integral of x squared, it would be x to the 3 over 3. So often, if you look at it in your memos and stuff, it'll just say a third x cubed, because x cubed over 3 is a third x cubed. Okay, so that would be an example. Another one could be x to the 4. Okay, now if you've been following along, I'm not going to do the colors now, but we add 1 to that 4, which will be 5, and then we just divide by 5. Okay, simple. Let's do another one. The integral of, let's put a number in front of the x squared. So let's say 3x to the 2. What do? We add 1 to the exponent. The 3 just remains there. And then we added a 2 here. And so remember, we divide by 3 here, right? So it's a bit more confusing when there's a number in front of the x, but we just leave that number alone. Okay, so that we added 1 to the 3 and we divided by the 3 and we left the 3 alone. So let's do one more where we have it. So this 3 we actually just leave alone. Okay, and then the 3 over 3 cancels and you just left with x cubed. Okay, let's do one more. Let's do So 4. Let's do 4x to the 7. A slightly bigger number. What do? We add 1 to, we will, let's start with the front. We leave the front alone, so that's 4. The x, and then we add 1 to that 7, so that 7 becomes 8, and then of course we divide by 8. Okay, and then the final answer, 4 over 8, it simplifies to a half, and so we have a half x to the 8. Okay, so what are we doing? We're leaving the front number alone, we're adding 1 to the exponent, and we're dividing by the new exponent. Okay, so let's look at how that would look like with this little x here. So we would add 1 to that x. So the question was there. Let's do the yellow. Okay, so this x, we're integrating just x. We add 1 to the exponent. So 1 plus 1 is, so remember there's a ghost 1 here. So we add 1, so it becomes 2. And then we divide by that 2. And so we end up with a half x squared. So let's look at how that would, so that is the integral. Now, let's say from 1 to 2. So, sorry, from 0 to 1. So, by the way, I haven't, this is not the full integral. There is a plus c, but I'm going to explain that just now. If we have a, if we were to substitute in 1, yeah, so a half 1 squared, what do we get? We get a half. Okay, so let's actually go back and do the colors. So remember when we did the one in pink, the little triangle, right? That was from to 1. Well, if we were to substitute in 1 here, we would get a half 1 squared, which would be a half. And that's what we got here, a half. To 2, if we subbed in 2 here, 2 units, 2 squared is 4 times a half is 2. And notice, yes, we get the 2. Finally, we did the green. We didn't do it, but we said it would be 3 times a half times 3, because it was the base times the height. So 3 times a half, we get 4.5. Well, what happens when we put this in? We get a half, and then 3 squared, which is 9. A half times 9 is 4.5. It works every time. So this doesn't just work for the straight line. It can work for any type of function. So it's very, very handy. But what I want to do is just explain to you now that when you see the, well, let's look at, if we were to shift this graph up. If I was to shift it up till here. Not allowing me to move it. Right. Yeah. Okay, so notice that when I shift the graph up by 1, we have this area here that we suddenly have this new area under the graph. But of course, my slope hasn't changed. So how do I account for this new blue area? Because it's got the same graph. So if I was to, well, let's see what the integral was of that graph was. So the integral of the graph we remember was a half x squared, right? So in other words, it's the area, remember when we did integral of x, we added 1 to the exponent. And so the equation for the integral was a half x squared. So let's just go work backwards and say, well, what if I was to get my derivative? Well, derivative, as you say, the exponent times the front. Well, 2 times a half is 1. And take one of the 2. And you see that I get back to my x. So remember that the x, the function was f of x equals x. The integral was a half x squared. And if I get my derivative, so in other words, I go back, I get back to my x. So it's confusing. You have a function. When you find the integral, you find the area under the graph. Now, if I was to find the derivative of my integral, I get back to my original graph. And that is because derivative is the opposite of integration. One, you're finding the area, and then one, you're finding the slope. So when you're finding the derivative, you're finding the slope. When you're finding the integral, you're finding the area. And when you take your integral and you find the derivative of that integral, you get back to the original slope. The original function. So the integral of this graph, x, is a half x squared. And when we find the integral of a half x squared, we find the original graph. Okay, but notice something. The integral of the derivative of a half x squared gets back to the original. But this graph here is the new graph that we found is actually, do you see that it's the x graph, but it's shifted up by 1. So how does that work? Because I haven't, when I find the integral of this, I don't get, in other words, the slope of this graph is the same as the slope of this graph. And so what we needed was to know that when you have your integral, you need to have a c, which can be any number, because it could have been intercepting the y-axis at any point. It just so happened when I first did it, to make it simple, I intercepted at 0. But we need to know that it could be intercepted at any point. So, because I could have had +1, or I could have had +2 here. Yeah. And so this would be y equals x plus 2. And so there could have been any value that we would need to pop on here. So our integral needs to have a plus c here. Sorry, our answer has to have a plus c. And so this is just to say that now let's see how that would work. Okay, so when I go back to my original, if I wanted to find f of x, I need to say the integral is x squared. So it was a half x squared, because remember we added, so the integral, not f of x, let's do the integral of just x, right? We get half x squared. So that's the integral, but we need to say this plus c. And that is because the function could have intercepted the y-axis at any point. We don't know, because we can have any type of function. So we need a c there, which we'll get to. I think I should probably make some more space here. Okay, so I've cleared this now, and I'm going to just explain this plus C bit again, because I think that is probably the bit that's confusing. So when you find the derivative, so let's go back to the thing. So as I said, you need to watch the derivative video to understand integration. So remember that if we have an f of x here, the derivative of this graph is equal to a half. Is equal to 1, right? Because it's y equals x. And the derivative of this graph here, this is f of x. Yeah. So we'll make this g of x, remember, because we can label them differently. Well, the derivative of g of x is also equal to 1. So how do we distinguish between these two graphs? Because they both have a slope. Right, so if we went back to the original, because the graph, the derivative of, so in other words, the function, sorry, f of x, the function is x. All right, that's the yellow one. And g of x, the function is x. Sorry, the yellow was actually, we moved it up, sorry, is x plus 1, right? But remember, when we find the derivative of a number by itself that doesn't have an x is 0, right? So it would be 1 plus 0, which is 0. And then for the g of x, which is, this is actually intercepts, we'll say that intercepts at 2. So the 1 intercepts at 1, the 1. They both have the same slope because they're both parallel. But one intercepts at 1 and one intercepts at 2. So you have f of x equals x plus 2, f of x plus 1, g of x equals x plus 2, but you have the same derivative. But now the mathematics needs to allow for a different value here, 1 and 2. And so that is why we know that when we found the derivative, there was a number, there could have been a number by itself. But we don't know what that number was. It could have been 1, it could have been 2, but the derivative, when we look at it, doesn't necessarily tell us, as we see here. So I'll just put this. So notice that the derivative doesn't tell us what the intercept was, because it only tells us the slope. Now, what that means that our integral, which is the opposite of our derivative, could possibly have a number by itself, that 1 or that 2, but we don't know what that was. And so we just have to put in a C, and C represents that number. So that is why, I hope that makes sense. So that is why when we have f of x, the derivative of f of x, we use that formula, which was the f of x, and then we add the n plus 1. So that was an n here, and then we have a divide by an n plus 1. We have to pop on the c. You have to say plus c always. And that c represents what the intercept could have been. So when we find our integral, we always have to be aware that there could have been a c here. And it's difficult when we are finding the area under a graph, because, as I say, the C we don't necessarily know. So the area under these graphs, if I was to go from, say, -1 to 2, would be the same as if I went from -2 to 1, right? These are the same, these would be the same size triangles. Or if I went from -2 to 2 on the yellow graph, over here, it will be different to the area under the graph from -1 to 2 on the green graph. Okay, so it's not so simple when we are dealing with different functions. And so instead of having what we call the indefinite integral, so the indefinite integral is when I don't define the area under a graph. So when I found the integral, remember, of that x to the half, sorry, the y equals x graph, which was then half x squared, we noticed that if I put in 1, I got the area of that one little triangle. But that only worked because I used a simplified version where the graph just happened to intercept the y-axis at x. But actually, it doesn't always do that. And so now we introduce what's called the definite integral, which is where I define the area on the graph that I'm going in between. And so what I do for my definite integral, is I actually put the 2 points where I'm trying to find my area. So let's say I wanted to find it from the integral of, so the area under this graph here. So let's do it from here. So the integral of this function here, which is yx plus 1. So the integral of this x plus 1 is going to equal, I add 1 to the exponent and I divide, and then 1, if I have an x to the 0, if I add 1 to the 0, I will get 1. And then if I divide by 1, I will get 1. So that is the key here to this, is that, and then I have to put a plus c in, remember, because I don't know. So here I have my new integral. And so I need to get the definite integral. And so what is a definite integral? It just adds the 2 points. So I could say from 0 here to 2, right? And then I can sub in those values. And so what I do here is I put the 2 to the 2 over 2 plus 2 plus c minus, and then the 0 squared over 2 plus 0 plus c. Now, the beauty of this is that, so this, the one in purple is the 0 bit, so I'll do that, the n0. And then the one in, we'll make this green here, so 2 here, that's 2. Do you notice that when I subtract these from each other, the c's go away? And that's the key to this. Because when the c's go away, I then can get the area. So I don't have to worry because the c's are cancel each other out. So when you find the indefinite integral, you always going to have to write your c in. All right, so we did that here if it was an indefinite integral. So before we wrote the 0 and the 2 there, we just found our indefinite integral there, the x squared over 2 plus x plus c. We have to keep the c in, okay, because we don't know what the you know, we don't know what do we call it, the variable, the variable was, but it doesn't matter when we are finding the definite integral because the c's go away. Okay, so if we sub in 0, 0, 0, we actually get 0. And then 2 squared is 8, sorry, 4, divided by 2 is 2, plus 2 is 4. Well, that should work, because then if we look at this from 0 to 2 here, this bit here is 2. And then this bit here is wait, why did I have a plus? Oh, because I went to 2. And then here, it'll be 2 and 2, right? Sorry, 2 and 3. And so it'll be, wait a minute. Oh, I'm doing the wrong to the 2. I need to, oh, so x was 2 here. Should be 4. Oh yeah, that is right, because here we have this point here, if it was y equals x plus 1, if this point here is 2, and this, then the y value is 3, right? Because it's 2 plus 1 would be 3. So the height of this triangle here is 2. And so the base is 2. And so then it's 2 times 2, which is 4, for the half of the triangle. So in other words, if I go back, this does work. So let's do it here. So this 2 here, this represents this rectangle, which is 2 by 1. And then this 2 squared over 2 is this triangle here, which is a 2 by 2 triangle. And so 2 times 2 is 4, times a half is 2. And so we end up with 2 squared over 2, which is the 4 over 2, which is the triangle. So this is the triangle, and this is the rectangle. So let's do it. Let's do the one more. Let's do it for this green graph. Okay, so we'll go back, go all the way back to the beginning. Okay, and so we'll do the integral of the green graph. So we have the green graph is g of x equals x plus 2. So remember, the integral, we're trying to find the area. So we'll say the integral of g of x, okay, that's the notation here, is equal to, we add 1 to the exponent and we divide by 2. And then the 2, remember, if it's just, it becomes 2x and then plus c. We just need to add that plus c on. Now, if we find the definite integral, all that means is that we finding it from an area. So we'll do the same. We'll do it from 0 to 2. And so what we have is, we'll start with our 2 squared over 2 plus 2 to the 2 plus c. And we'll subtract the other one. So we'll make it from 2 to 0. And we'll subtract the 0 squared plus 2, 0 plus c. And we notice that the c's will cancel when we subtract. Now this bit on the side is 0. And we have then 2 squared, which is 4 over 2 which is again 2, and then the 2 times 2, which is 4, and then the area is equal to 6. Okay, now let's go. So the 2 is the triangle. Again, the triangle here. So we're looking at the green graph, the area of the green graph from 0 to 2. So you see that there's the triangle, which is a 2 by 2 triangle again, which is 2. And then notice the 4, because this base is 2 and this height here is, is 2, yeah. 2 and 2. And so we have 4. That's 2 by 2 triangle, which is 4. Okay, I think because it wasn't to scale, that is where the confusion came in, but we can see that's the rectangle and that's the triangle there. And so this integration works for a number of different functions. So what we're going to do is we're going to do one more, and we'll do just show that it doesn't necessarily just work for straight line functions. Oh gosh, what did I do? So let's have this function. Oh. Okay, we'll just do a quick function here. So this will make this intercept. So we'll make this the y equals minus x squared graph. We'll just add 1 to it, make that 1. So what I could do is I could find the area under this graph here from -1 to 1. Well, all I would need to do to find this, and now this is much more complicated than straight line graph, I cannot use triangles, is I need to find the derivative, the integral. So what I do is I'll say, I'm going to find the integral of this. Okay, so we'll start by just doing that. We won't find the definite integral. Okay, what do? We add 1 to the exponent, so that's 3, and we divide by the new exponent 3, and then we say plus x, because the integral of 1 is just x. If it was 2, the integral would be 2x, and I have to put the plus c. Okay, well, I don't need the s anymore because I've actually found the integral. I don't know. It used to be able to allow me to erase these things nice and easily, but it keeps erasing the background. Okay, so that is the integral. So that would be the indefinite integral. So if I was to put 1 in here, I would get 1 cubed over 3 plus 1, which would equal -1/3 plus 1 is 2/3. Now, that actually happens to be the integral, the area of this here, 2/3. So that is that, but there, that 2/3. But it just so happens that the indefinite integral works it out because it goes from 0 to 1. Now, if you were to subtract the integral, so in other words, if you went from 1 to 0, when you subtract 0, when you substitute 0 in there, you're simply just subtracting 0 anyway. We could say plus c here. So let's look at how it works when we want to find the integral from 1 to -1. So we'll go 1 to -1. Well, let's start with 1. Well, we've already done 1. All right, this was 1 here. When we put 1 in here, we got 2/3. So I'm just going to say 1, just to make our lives easier so we don't have to do it again. Minus Okay, but it was 1 plus c. And then we minus, and let's go to, let's do the next one, pink, so to minus 1. So technically that this bit here is actually just here. And then to minus 1, and so we'll substitute a negative 1, so negative 1 cubed 3. And then when we substitute minus 1 into x, we get minus 1. Is that right? Yes. Let's see. Okay, so again, we notice the c's go away. So that's why definite integral is handy. Now, minus 1 cubed is minus 1. Minus a minus is a plus. So we end up getting a third minus 1, which is minus a third. Minus, hang on, we get a third here. Minus 1 is minus 2/3. So this pink bit is minus 2/3. You can check it on your calculator. Now, when you minus a minus, you get a plus. So you end up getting, we know that this was, sorry, this wasn't 1, this was 2/3. So we end up getting 2/3 minus 2/3. We end up plusing 2/3. Then I'm getting 2/3 plus 2/3. Well, of course, because this is a positive area. Okay, so that's integration. It's quite confusing. The main point about it is the formula, adding 1 to the exponent and dividing by that new exponent. And then the next thing is to make sure that you have a C. All right, so that's your introduction to integration. Integration, to summarize, is the area under a graph, and differentiation is the slope. Okay, so any questions? We'll revisit this again and we'll do some examples, and hopefully anything that wasn't clear will be cleared up.